Hello, good afternoon, or good morning, whenever you're watching this, everybody. My name is Jonah Schulte, and today we'll be talking about PerfFuzz, the multi-objective automatically generating pathological input device software. This presentation is based off a research paper by Caroline Lemieux, Koushik, Rohan, Padhye, and Don Song, and obviously it's presented by me. So, firstly, worst case behavior is both the bane of a programmer, but also kind of the same friend of a programmer in of course, certain respects. Performance problems can arise unexpectedly all the time from software when provided with unusual inputs. For example, those that can make worst case behavior appear. There has been a lot of research on finding out what types of inputs can execute the worst case behavior. Most of the research has been done using statistical profiling or learning about the code in depth and trying to find inputs that would directly affect the program from their educated guesses, basically black box versus white box fuzz testing. Enter PerfFuzz, which is the topic of this research paper. PerfFuzz automatically generates inputs that make or give pathological behavior without any prior knowledge of the code itself. PerfFuzz works unlike other approaches, which would usually attempt to maximize a scalar characteristic. An example of a scalar characteristic would be something like the total execution path length. So, unlike others, PerfFuzz uses multi-dimensional feedback and also makes sure that every program location is executed or worked the maximum amount of times that is possible. So PerfFuzz can, 1, find multiple different inputs that exhibit worst case inputs for a given program, and 2, generate inputs with higher total execution path lengths than previous fuzzing tools. PerfFuzz can also kind of work as a sort of a debugger by showing weaknesses in the program and, their poor time complexities. The researchers for this paper, which I will abbreviate to be calling SSLP, implemented PerfFuzz on top of a previous fuzzing instrument called AFL, which is the American Fuzzy LOP, which is really just a generic fuzzing device. They used 4 real-world C programs that are usually used to test fuzzing for evaluating how PerfFuzz works. And in the end, PerfFuzz really just ran off and did a lot better than any of the competition that it was put up against. So, introduction. Performance problems in software are so common, so well hidden, it is like that's all they spend their life doing. Well, I guess it is all that they spend their life doing, but either way, almost every programmer wishes they would just not show up at all. Besides, there's funny fails that can happen for homework programs. There's also, more serious fails, work projects that are meant to carry serious information, or possible hospice software that people's lives depend on, especially in this current unfortunate climate with COVID-19 running rampant. They need to make sure that there won't be a denial of service, an accidental denial of service attack because of some random input that throws the whole machine out of loop. So it has become common practice for testing software to include fuzzing tests, both black box and white box fuzzing, which I mentioned before. But it's also fuzzing is when inputs are thrown into a program to see what happens. The goal is to try to activate the worst case behaviors of a program. Black box and white box fuzzing are basically, I don't know anything about this program, so let's throw as much as we can into it to see what happens. And I know everything about this program, so here are a few test cases I know will cause some kind of chain reactions. Besides just programs not working efficiently, there's also there are security flaws. that can be shown through fuzzing tests. Those that have algorithmic complexity vulnerabilities. And that's how actual DOS attacks work, as they cause a running program to exhaust all the resources when given untested worst case inputs. And then there's also user fuzzing, which is when, after the software has been released, users send in inputs that create worst cases that the programmer missed. Unfortunately, the user inputs and most other inputs, while they appear to give worst case inputs, they actually just give closer to average case inputs. A certain class of inputs from whichever fuzzing type, black box, white box, or user, are called pathological inputs, and these are the best kind of inputs for worst case testing. So they're the worst kind of inputs because they make worst case, but they're the best for making worst case. And the reason why is simple. They actually do give the worst case tests, and they also do it in different parts of the program, not just on one specific traveled row that always happens to make a big problem. An example of a pathological input would be when using hash tables or sorting algorithms like quicksort. Pathological inputs for a hash table would be when there is an input that gives the maximum amount of collisions on the hash table, while for the quicksort, just the input that gives a lot of swaps, like a reverse, like an array or an input that was reverse sorted. Pathological inputs maximize the execution count of a specific program area. So introducing PerfFuzz, the main goal of PerfFuzz is to create pathological inputs for any program without any previous knowledge of that program. It achieves this goal by generating inputs by feedback-directed mutational fuzzing. Feedback-directed mutational fuzzing is when new inputs are created by mutating a previously saved input, as well as new inputs are saved if they go through a new area in the program's code. Mutating inputs can be as simple as flipping bits of a string of input numbers, or rewriting a copy of a picture with semi-valid bits that were shown previously. PerfFuzz's main idea is to associate each program location to an input that exercises the location the most. And so when PerfFuzz gets back the information from the inputs that it executed, some that exercise a certain location more than other previous inputs are kept, while some of those are mutated and some are just thrown by the wayside. PerfFuzz is able to amass a variety of different inputs that hit different hotspots, which can be described as certain places in the code that are usually executed more than most. SSLP planned to work with 4 different C programs for this paper and check the results against other fuzzing tools to see which of the programs perform the best out of all of them, whether it's PerfFuzz or something, a different software that PerfFuzz was up against. It is worth remembering that PerfFuzz can also help with dynamic analysis and debugging flaws in the algorithmic complexity and its vulnerabilities. And so PerfFuzz will also be tested against SlowFuzz, which also tests for algorithmic complexity vulnerabilities. So here's an overview of just how PerfFuzz works in general. So this program is a simplified version of WF, a word frequency counting programmer. The main program driver takes an input string, splits the string into words at the white spaces, and counts how many times a word appears. A simple hash table is used to map words to their integer counts, which would be at line 11, as you can see. I hope you can see right there. This program works excellently with any input containing only English text, as there are no performance bottlenecks or repeats of the same line over and over again, or pauses in the code because it's trying to figure out what is non-English letters. This is because most English words are usually short, so there's no going over and over and over and over again. trying to compute the hash function, like at lines 14 to 20, which is in compute hash method there. Or the number of different words isn't that large either, less than 1,000, which is, less than 1,000 distinct words in the English language. And yeah, so a second case could be when there are many different distinct or different words, thus making add word an often used function. As you can see, it's line 22, that whole function. Add word, you have to check and see if there's a different word. We're just continually adding words for each new word. And if it's just a long sentence of different word after different word after different word, add word keeps going over and over and over and over and over again. So that would be a performance bottleneck for this program. It would highlight that, oh, okay, if I give it this input, it could potentially be stuck there for a long time, possibly opening the door to like a race window or a talk-to attack possibility. This is where we see, add word is also where we see each letter in a word iterated over and over again, so it's even longer than you think. So how is this relevant? Well, how does SSLP find these kinds of performance bottlenecks? If inputs like so were available, they could run this program and throw those inputs through Valgrind or gprof32 and see the source locations where the program spends most of its time. These inputs would highlight where the program is spending its time through Valgrind. There are so many things to learn too. Maybe they could use a statistical bugging tool to compare what inputs make the program faster or slower. But that's basically what PerfFuzz is for. Hopefully that's what people would start using PerfFuzz for now, to create and find these inputs that highlight these bottlenecks. So the goal for this research paper was to create different inputs. Oh, that's supposed to say was to create different inputs that maximize the execution count of each edge that was in the program. We can assume that we have one or more general seed inputs that are common inputs for the program. PerfFuzz usually mutates them and then use their children to create the worst test cases for the program. SSLP used about 4 seed inputs for its testing, but mostly it was just one input to start PerfFuzz off. The basic outline of PerfFuzz is as follows. Initialize a set of parent inputs, seeds, find which input maximizes an execution count for a control flow graph edge, which you'll hear me talk about as a CFG edge or just an edge. From that input, create multiple children inputs added by mutation, which could be flipping bits, removing or inserting byte sequences, or splicing the parent and the child input together, and then continue that until the time limit is reached. So just to give a little bit more about an example of how PerfFuzz works, we're going to go over that WF program through PerfFuzz, or with PerfFuzz. And the input seed would be the string, the quick brown fox jumps over the lazy dog. So here's the program again, well, the majority of the program we need to worry about. And there are 4, seed inputs for the program right there. So the first one, the first seed, the quick brown fox jumps over the lazy dog. There's nothing really worst case-ish about the sentence. 8 distinct words that really aren't large words, so there's really nothing special about that first sentence. So after running the program and the input, the quick brown fox jumps over the lazy dog, the result is that add word is invoked 8 times, whereas the true branch line of line 20, true branch of line 29. Oh, I'm sorry, I accidentally hit my microphone. Is only executed once, which is after the while, and it's the if. The statement of the if string compare e to key is word equals to 0. That's only executed once. For the two thes in the sentence, the quick brown fox jumps over the lazy dog. So after that, PerfFuzz mutates the sentence as shown in the second one here, from the quick brown fox jumps over the lazy dog to the quick brown fix jumps over the lazy dog. This doesn't increase any execution count, so it is discarded like most mutated inputs, because it doesn't do anything new. The next mutation is just removing the I in quick and leaving a blank space, so it would be the brown fox jumps over the lazy dog. This does create an extra word, so add word is increased its amount of execution again. And since there is a change to the number of CFG edges being hit because add word was hit again or executed, this input is saved. In the final example, the quick brown fox jumps over the lazy dog, dash underneath. It's removing the space and adding an underscore between brown and fox. Funnily enough, the word brown fox and dog have the same hash value, leading to a collision, so this input is saved as well. You'll probably have noticed that adding the underscore actually decreases the number of words, and this is important, so we'll return to it in a second. So inputs that are saved become new parent inputs, and their children are basically just mutated versions of themselves. And this continues with children becoming parents and creating children until the time runs out, so to speak. Any inputs that maximize execution count of a word of an edge is saved. However, it should be noted that there may be a new input that only maximizes a certain edge, but also does it more than a previously saved input for maximizing a certain edge. The old input is then ceremoniously replaced, and you may be wondering, how can something maximize an edge if it's already been maximized? Well, there's really no actual definition for maximize. Like, there's no, this part of the program can only be run this amount of times. It can only be run as many times as possible. So it's just the maximum amount of the last set of inputs that were run can be upped by another maximum that's higher than the previous maximum. I hope that makes sense. The number of inputs is always smaller than the number of edges, and this is obviously because there may be singular inputs that maximize multiple CFG edges. So really there's no need to have one-to-one correlation between edges and maximizing inputs. Since most mutations will not increase maximum edge selection, PerfFuzz can do massive amounts of work in a short time. With the word frequency program we just were talking about, PerfFuzz was able to do 6,000 inputs in a second, making 20 million inputs in an hour. Just testing to see what would make those worst case executions, and also find the total path length. So here's some interesting results for the final, just a few of the final inputs that PerfFuzz made. I wouldn't be able to read most of these sentences. I don't know any human alive that could, but I will give it my darndest try. These are a few of the favorite inputs for WF that PerfFuzz spat out at the end. The first one is just an extremely long word, and it maximizes the execution count of line 17 in compute hash. So down on the compute hash side, TVC1 PFEJ question. I'm not going to say anymore. So the second one is just a bunch of small words, and that maximize the execution of add word. If you can see that there's a T, but then there's a bunch of spaces after basically each word. I mean, it's T, 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 I, N, V, T, X space. Just a bunch of spaces, so it really maximizes that add count of, okay, we need to check it again. And finally, this last input is very interesting, because the last one contains many words that hash to the same bucket T, which exposes a worst case complexity because it has to traverse a long linked list. I mentioned earlier that we were talking about less words still being viable, or about how because one input made less words, that isn't a problem. Because PerfFuzz is still inclined to say for maximizing edge execution rather than total execution path. It doesn't mind. I mean, it's not that it doesn't mind total execution path. It doesn't think total execution path is bad or unhelpful, but it's a little bit more focused on maximizing the CFG edge execution. Most other fuzzing software, like slow fuzz, which we'll look at later today or later in this presentation, and AFL, it uses greedy algorithms, and that's really only considered the total execution path length. When PerfFuzz puts its focus on the edge execution, it can still find the worst case behavior even when the program execution is non-convex. Okay, I should just mention earlier, I also accidentally hit my mic again. I'm very expressive when I talk, so I have to use my hands a little bit, and every once in a while, with my mic so close to my face, I accidentally touch it, so I'm sorry. I will try to keep that to a minimum. But if you do hear that, that's just me accidentally waving my hands around when I'm talking and hitting my mic. Okay. So now we're just going to get into the algorithm they created for PerfFuzz in itself. In broad terms, the goal of PerfFuzz is to generate inputs that achieve high performance values. Oh, that's my dog. High performance values in certain program components. We make the execution counts the high performance values and the CFG edges to be program components in this case. But that's not the only parts we can define as program components. PerfFuzz can be adapted to many parts of a program. So this is the step-by-step version of the PerfFuzz algorithm. PerfFuzz is given a program small p and a set of initial seeds, which are used to create the first parent set of seeds, big P. The inputs in big P are set to be the base of the mutations after the first input is executed. PerfFuzz then considers each input from big P and decides which of them to mutate. There is a selection probability method called fuzzprob that assigns a value to an input to see if it should be mutated or not. Considering when it considers each input from big P. An assigned value of 1 means that it will be mutated. Otherwise, it's a low possibility that the input will be mutated. For every parent input that is chosen for fuzzing, PerfFuzz has to determine how many children that parent input should make. Children are created through the mutation, as mentioned before, but the number of children to be created is implementation specific. SSPL used AFL, as mentioned previously, so they let AFL and its standards decide how many children to make. I should just remind everyone that SSPL is the combined name of the researchers I'm using, so I don't have to say the researchers every time that I'm talking about them. PerfFuzz finally executes the program using the child inputs it created, the mutations, and collects feedback on the executions. If a child input makes the program work in a new line of code or maximizes the value of an execution, it is put into the set of parents for the next input. You might be thinking about how the importance of new coverage in a program isn't as important, especially after the words I said about caring more about edge execution. However, we were just talking about how PerfFuzz doesn't only work with CFG edges. It can be assigned to anything else. So knowing the inputs that gain new code areas aren't really bad to have either. This algorithm basically continues until the time allotted has expired. So this is just basically the algorithm I just described to you. You can see at line 1 right there, we have the seeds becoming the parent input seeds to big P. Line 4 shows PerfFuzz checking every parent input to see if they are, well, that would be line 5. Yeah, I'm sorry, line 5 is checking every parent input to see if they were mutating, deciding at line 5, yeah. Line 6 is where both the decision of how many children there will be for an input, and for each of those children, they must mutate each child, which is at line 7 of the parent. Num children is a method taken from AFL to decide how many children there should be. And line 7 is where the mutation happens, which is a PerfFuzz algorithm that we'll talk about in a little bit. Line 8 is where the actual execution of the program takes place. You can see run equals to goes to the feedback. And line 10 shows which children are added to the parent seed group for future fuzzing. Notice nucov and numax there if nucov feedback and numax feedback, or numax feedback, then you put it into the new parent group, which is what they're supposed to be, new coverage in a program and a new maximum edge selection. And 912 just shows that the time limit is again the reason this program would ever stop. Okay, sorry about that pause. I'm not sure if that'll be an instantaneous pause or not, but kind of had to remind everyone living in my household that I'm recording right now. Quarantine due to COVID virus, and my entire family is at my house. So, they could have just texted me that my food was here, but instead they decided to come in my room. Where were we? Yes, the third part of the algorithm. So we have to define certain concepts to explain how numax, defining or finding, I guess would be a better word, a new maximum execution of an edge actually works, and for an input to be favored to be mutated. So definition 1. A performance map is a function perf map, K to V, where K is a set of keys corresponding to program components, and V is a set of ordered values less than or equal to corresponding to the performance values at these new components. I should also mention that this gets into some pretty interesting math. Interesting is a funny word. Pretty intense math. And I'm just going to show you guys. I mostly understand, but I'm just going to show you guys and not try to get too deep into it. Okay, so when given a K and V, perf map of I is a performance map of the given program with input I. K and V have been left deliberately abstract to be flexible, with different program components instead of just different components. Like, people will think about CFG edges as the components for this. However, it could be many other different things. It could be like I/O executions. So definition 2, the cumulative maximum map at time step t is a function cumulamax of t from K to V. It maps each program component to the maximum performance value observed for that component across all inputs generated up to time t. Precisely, if it is the cumulative set of inputs executed up to time t, then that is what it says for an input in K. The cumulative max of time t is K is equal to the max performance map with input I of K. Definition 3, the function numax will return true for a newly generated input I at time step t if the following condition holds. Yeah, it's just it's just saying if there's an input there that is greater than the current max from k, if there's if a new input that makes a greater execution count in k, it would be returning true for the new max and be assigned to the new maximum. So this is the basis for the fundamental concept of PerfFuzz to achieve its testing goal. Recall that in line 10 of the algorithm, that if there is a new maximum or new coverage, that input is added to the parent group, large P. Coverage is implementation specific, so we'll touch on that a bit more when we're talking about the actual implementation that SSLP went with. One of the features that make PerfFuzz work is that it saves inputs that create a new maximum compared to previous values. In thinking about cumulomax, an input has a new maximum. Let me just look at definition 3 right now. A one element in the K that has a value has a greater max edge execution than the current cumulomax of the same program. So the second big idea of PerfFuzz is selecting the parents that should be mutated. In order to talk about fuzzprob, the method that assigns either the 1 or something else to show the probability of an input being chosen to be mutated, we must first define favoring in reference to PerfFuzz, specifically, of course. An input I maximizes a performance value for some component k if and only if its performance profile registers the maximum value reserved for that component. So far, an input I is favored for fuzzing at time step. So far, this first equation and definition 5, an input I is favored for fuzzing at time step t if and only if it maximizes a performance value for some component here. The favoring mechanism allows PerfFuzz to choose inputs that are maximizing performance values of certain program components. SSLP chose maximizing performance as part of the search because they believed that these led to expensive resource usage in those program components. And so inputs derived from inputs that already made maximizing performance values are likely to contain the same characteristics as their parents. Using this, we can define how fuzzprob works, which is definition 6. Definition 6, the selection probability of an input I at time t is 1 if favored, or just alpha otherwise. So, the implementation, SSLP's implementation of PerfFuzz is based off of AFL, so a lot of implementation details are inherited from the American Fuzzy Lab. I should also just mention that while practicing for this presentation, recording it, and currently myself right now, I'm having problems not saying ALF or ALF, just because I'm used to saying ALF instead of AFL. So if I say ALF or ALF accidentally, please don't judge me that harshly. So two specific things about the American Fuzzy Loop is they choose the number of child inputs to produce, and they like mutating inputs, though they don't mutate. It's almost exactly the same as PerfFuzz. These first two, mutating are from AFL, and the former having the heuristic about producing children only for the parent inputs that get wider code coverage, or discovered later in the fuzzing process. And for mutating inputs, PerfFuzz doesn't actually view its inputs other than a sequence of bytes, so all mutations are done at byte level, which PerfFuzz inherited from AFL, obviously. PerfFuzz mutations are a specific type of mutations. They're called havoc mutations. Let I be the parent. Choose a number m of mutations to apply. M is chosen randomly from powers up to between 2 and 128. From I of O equal to I, produce a series of mutated inputs I of j, which equal the mutate once I of j minus 1. The final mutated input is I prime equaling to I of m. The examples of some mutations for mutate ones are byte or bit flips at random locations, setting bytes to random or extreme values, 0 or the max integer values at random locations, or deleting and cloning blocks of bytes. The final mutated input is returned to the main fuzzing loop of line 7, being assigned to the variable child there. And mutate once chooses any of the one-step mutations that I just spoke about and applies it to the input I. PerfFuzz retains AFL's input splicing mutation stages. This is also called a crossover mutation. For parent I, a splicing mutation chooses a random input I prime in big P and pastes a random subsequence from I prime at a random offset in I. Crossover mutation only really runs when PerfFuzz has not recently found a new worthwhile input. So basically it's a last resort PerfFuzz. It usually doesn't use it because PerfFuzz is really good at what it does. But it has it there just in case, all best laid plans. So again, in SSLP's implementation, PerfFuzz uses the same new coverage definition as AFL, which works as follows. AFL inserts tags into the program that assigns an ID to each edge in the control flow graph of the program. During the execution, an 8-bit counter is used to keep track of each time an edge is used or traversed, and a new input has achieved new coverage if it visits a new edge or increases the hits enough to change the bucket position. And what I mean by that is AFL keeps a number of hits only to 8 buckets in like a hash table or map, I guess. The first 3 buckets contain it's hit the edge 1 time, it's hit the edge 2 times, and 3 times respectively. The next 3 are 4 to 7 times is 1 bucket, 8 to 15 times is the next bucket, and 16 to 31 times is the 6th total bucket. The last 2 buckets contain 32 to 128 times, and the last bucket is 128 to 255 times hit. The coverage definition was really just so successful in AFL that SSLP didn't want to change it from the original source. It should also be noted that with this definition, a new coverage does not necessarily mean a new maximum, and that's also true vice versa. We'll only talk a little bit about the performance map. It's a lot to get into, so we're just going to brush over it a little bit to save a little bit of time. SSLP's performance map is augmented off of AFL's LLVM mode instrumentations, which inserts the performance map created by SSLP into LLVM IR, SSLP being the researchers. Additionally, their augmented instrumentation creates their usual coverage map with the 8-bit hit counts, as spoken about before. I just want to remind everyone that PerfFuzz saves inputs that achieve the new code coverage to be used as parents for mutations. So, after we'll talk about the implementation of PerfFuzz, we're going to talk about how they evaluated PerfFuzz to see how it works against other software that basically already does its job. PerfFuzz was put up against SlowFuzz, which is basically does the same thing as PerfFuzz. It was written to be the same way, and 3 fundamental questions are asked and are going to be answered in this presentation. How does PerfFuzz compare to the single objective fuzzing techniques used in SlowFuzz? Is PerfFuzz more effective at finding pathological inputs than other fuzzing techniques that are rooted in being guided by coverage? And does the multi-dimensional objective of PerfFuzz help find a range of inputs that exercise distinct hotspots? The 4 programs, the C programs that I was telling you about that we're going to evaluate or test, they're pretty common in fuzzing tool testing groups. There's the libpng, the 1.6 version, the libjpeg turbo, the 1.5 version, the zlib, the 1.2 version, and the libxml 2.9 version. These programs were chosen because, like I said, they're commonly used in checking fuzzing benchmarks, and they also are pretty large. They have a lot of code. There's 9K lines for zlib, 30K for libjpeg and libpng, and actually 70K for libxml. And they also had readily available drivers for libfuzzer, a LLVM-based fuzzing tool, which we just talked about. And the implementation of the performance map was based off of LLVM, so it worked out for SSLP perfectly. And libfuzzer made it easier to more fairly compare PerfFuzz and slowfuzz, as unlike with base AFL tools, libfuzzer relies on a specialized driver that directly takes in a byte array and doesn't depend on any global state and never exits from any input. The drivers chosen exercise the PNG read function, the JPEG and zlib decompression function, and the XML read from memory function. PerfFuzz was ran for 6 hours on a maximum file size of 500 bytes and with sample inputs that came with AFL for each program. 500 bytes was chosen for the maximum because it was the upper bound on all the seeds that were considered. The 6-hour run was repeated 20 times to account for non-deterministic fuzzing, for the non-deterministic fuzzing tool of PerfFuzz and AFL. So the second part of the evaluation was testing PerfFuzz and finding worst-case algorithmic complexity as a function of varying sizes. 3 tests were given. Insertion sort. Insertion sort was decided as one of the inputs as it was the only default example that slowfuzz had for testing in its library. Matching an input string to our URL regex using the PCRE library. And WF version 0.41. WF.41 is basically the same word frequency counting tool that we showed in this presentation earlier. These 2 values allow SSLP, the 2 values being maximum path length and maximum hotspot, to accurately create graphs to compare PerfFuzz to its competition. So for the maximum path length and maximum hotspot, these are the definitions of them. If E is a set of edges in the program under tests, and I is a set of inputs generated by the fuzzing pool up to time t, definition 7, the maximum path length is the longest execution path across all generated so far, seen there with the maximum sum value. And definition 8, the maximum hotspot is the highest execution count observed for any CFG edge across all inputs generated so far, the maximum hotspot equaling the maximum of the perf map. This also allows SSLP to get a grasp of the path length, as well as whether that is driven by a specific program component, this being a hotspot, without having to look at the entirety of distribution of the execution counts of the edges, which, is not the least bit practical to do for any reasonable amount of time. So, comparing it with slowfuzz in the first part we were talking about with the 4 C programs. Slowfuzz is a tool much like PerfFuzz, producing inputs that expose vulnerabilities and algorithmic complexities. Slowfuzz is also like PerfFuzz because it is also an input format agnostic fuzzing tool for C or C++. So, SSLP chose it because it was most closely related to their idea or implementation of PerfFuzz. Unlike PerfFuzz, slowfuzz is one-dimensional in its objectives, as its goal is only to maximize the total execution path length for a program. There's another reason why slowfuzz is a great candidate, as comparing the single objective software versus PerfFuzz's multiple objective idea. There are 2 main algorithmic differences between slowfuzz and PerfFuzz. PerfFuzz creates at least thousands of inputs from seed inputs, while SlowFuzz produces only one mutant for each parent. This would reduce the importance in SlowFuzz for selecting which input to fuzz. PerfFuzz must choose from a huge number of inputs to fuzz, and will usually only mutate the favorite ones. And since there are less inputs from SlowFuzz, it's a lot easier to choose at random. A lot easier on the program. If you just think about that for a second, if you have 10,000 choices to pick from, and there are a couple of them that you've already tagged, you're like, all right, let's go. I'm going to pick those 25 that I've tagged because I saw they worked really well. However, if you have like 100, you're like, well, I guess I could spend some time just, oh, you, and you get like however many you need. PerfFuzz uses having mutations on its inputs, while SlowFuzz keeps track of which mutations were more effective before and uses them again on later inputs. SlowFuzz is built on libfuzzer, which we mentioned previously, which was used before to help build the performance map. So SlowFuzz runs a bit faster than base AFL, which is what PerfFuzz is based on. In this case, SlowFuzz would actually produce more inputs than PerfFuzz in a set time span. This didn't really concern or worry SSLP, as they ran SlowFuzz and PerfFuzz for the same amount of time, and it wasn't that big of a difference, as you'll see. So there were two fronts that SlowFuzz and PerfFuzz were compared on: maximizing execution counts and their ability to find inputs that demonstrate worst-case algorithmic complexity. In every run of SlowFuzz, they used the example inputs found in the example directory. There was a partial exception to all of them, as they used a strategy called a hybrid mutation strategy, which was also used to test SlowFuzz itself. So these are the results. This shows the progress made by PerfFuzz and SlowFuzz during 6-hour runs in maximizing total path length on the left, and maximizing hotspot, which is the graphs on the column on the right. The lines in the plot represented average values over 20 repeated 6-hour runs, while the shaded areas represent 95% confidence intervals, calculated with students' t distribution. As you can see, PerfFuzz completely outperforms SlowFuzz in every competition. PerfFuzz finds inputs that are significantly worse performing than SlowFuzz by both metrics. And it should be remembered that SlowFuzz actually produces more inputs in every test, from as many as 1.7 times more than PerfFuzz with XML, and 17.7 times more inputs for JPEG. The maximum path lengths found by PerfFuzz are 1.9 times to 24.7 times higher, and the maximum hotspots are 5 times to 69 times higher than those that were generated by SlowFuzz. SSL believe this is because of the use of the greedy algorithm in SlowFuzz. A greedy algorithm with respect to maximizing total path length is likely to get stuck in local maxima. Thus, in contrast, even with PerfFuzz saving newly generated inputs that could have less total path length, as long as there is an increase in the execution count for the edge, of course, PerfFuzz's multi-dimensional objective allows it to perform better global maximization of total path lengths. These results show that PerfFuzz is better than SlowFuzz at finding hotspots, which is what PerfFuzz was truly made for. But it also performs better than SlowFuzz at finding inputs that maximize total path lengths, for which SlowFuzz is tailored, because, SlowFuzz keeps getting caught on the local maximum because of its greedy algorithm. So talking about the algorithmic complexities evaluation / test that SlowFuzz went up against PerfFuzz for. SlowFuzz was designed to find the algorithmic complexity vulnerabilities, where programs exhibit worst-case behavior that asymptotically worsen their average case behavior. Every knows programs with problems like these. If accepting untrusted inputs, an attacker could carefully send a crafted input that took advantage of the worst case complexity, and make denial of service attacks occur. After the tests with SlowFuzz and PerfFuzz on these types of inputs, we know that PerfFuzz can address these problems and can outperform SlowFuzz in some cases. To reiterate, for these cases, the tests were insertion sort on an array of 8-bit integers. This was, again, the only benchmark provided in the SlowFuzz repository to test itself. Matching an input string against a regular expression to validate URLs using the PCRE library. And WF 0.41, the word frequency counting program. All of these are exactly what was used to evaluate SlowFuzz, or at least they're very similar to the programs that were used to evaluate SlowFuzz at its launch. Each of the tests or benchmarks have an average case runtime complexity that is linear, and worst case that is quadratic. Insertion sort ran for 10 minutes, and PCRE and WF both ran for 60 minutes. In every case, a single input seed was given, a sequence of 0-value bytes of maximum length for both insertion sort and PCRE, truncations of the quick brown fox jumps over the lazy dog for WF, 20 runs for each of the benchmarks to count for any variability. SSLP measured the maximum path length observed over all the inputs produced in these runs. So these are the results. This shows the points plots the average maximum path length, while lines show 95% confidence intervals. For input lengths 10 and 20, for the insertion sort, Perf found the worst case would be a reverse sorted list, as mentioned earlier, while SlowFuzz put forward a non-zero variance in the results. It should also be noticed that for larger input sizes, PerfFuzz finds lists with more comparisons to sort than SlowFuzz. However, both did discover the worst case quadratic time complexity for the insertion sort benchmark, which is why they're both pretty close to each other. For insertion sort, all the path lengths resulted in PerfFuzz finding significantly longer path lengths, but as you can see, it's only minimal for small input lengths. In PCRE, we can see a major difference between the worst case inputs found by PerfFuzz and SlowFuzz. PerfFuzz consistently outputs inputs that lead to worst case complexity, while SlowFuzz only finds superlinear cases. Look at that example input there, the FHFTP : // It should be remembered that PerfFuzz was given an empty string with no knowledge of the program beforehand. That might start really making you think about how amazing PerfFuzz is. Looking at the PCRE graph, we can see that SlowFuzz performance has a large variation. The vertical line down near the 60 being so long on this test. This indicates that any real progress that SlowFuzz made was likely luck, as remember that SlowFuzz mutates its inputs randomly, so it is lucky that it got even far enough to be superlinear instead of relying on the staying regular linear, I guess would be the way to say that. And the last graph shows PerfFuzz clearly finds an input closer to the worst case complexity in the given time budget for WF. The reason WF is so hard to find a worst case for is because the worst case is only triggered when distinct inputs in the input string map to the same hash bucket. They start with a few words that are distinct, but they have the same hash code. And then a single one-letter word, as you can see down here, a one-letter word, the T, is repeated multiple times through that hash. That's one of the examples. The most amazing thing about these inputs is that they precisely exercise the worst case complexity. Let me explain how it hits WF right on the head with a jackhammer and how to puncture and get that worst case complexity. First, a small word is inserted into some hash bucket. Then, the next few words have the exact same hash code and are inserted at the front of the linked list in that bucket. the first word is now the last node in this linked list. Finally, the repeated occurrences of the first word cause WF to traverse the entire linked list multiple times. All slow fuzz could make had some hash collisions at the worst. Obviously, PerfFuzz outperforms slow fuzz completely in both trials. So this is slow fuzz and no, I'm sorry, it's not. They decided to take it further. That's right, SSLP decided to take it further and pit up PerfFuzz against its, parent, basically, AFL. AFL was run with the same inputs, benchmarks, and mutations, havoc in this case, as PerfFuzz. The experiment tests the value add of PerfFuzz's performance maps and maximizing input favoring heuristics. These graphs show the evolution of the maximum hotspot found by each software through time on lib PNG, lib XML, lib JPEG, and zlib. For PNG, JPEG, and zlib, we can see that PerfFuzz rapidly finds the hotspot with the highest execution count. For XML, AFL does beat PerfFuzz to a higher hotspot first, but then it quickly plateaus, as it does with the other tests as well, as you can see. On the same graph, on the other hand, PerfFuzz finds a hotspot with the 2 times execution count after 6 hours. So, in XML, AFL, beats PerfFuzz to the better execution count, I guess, but then it plateaus. However, by the time PerfFuzz gets up to where it needs to go, it's found one that's 2 times worse than the one that AFL sticks with. Overall, this demonstrates that PerfFuzz's performance map feedback greatly increases its correct work output, with the output being anywhere from 2 times to 18 times the execution count of its more than its predecessor. These graphs show only the execution counts for the maximum hotspot. As this is rather easy to visualize over time, SSLP wondered if the maximum execution counts found by PerfFuzz are significantly higher than those found by AFL over all hotspots in the program. Sorry, I'm giving myself a little drink of water. Okay, so comparison with coverage-guided fuzzing. These final graphs represented the maximum execution count per CFG edge found by each of the techniques, AFL and PerfFuzz, at the end of their 6-hour run. The omitted tails of the distributions are basically indistinguishable. The median is plotted across 20 repeated runs. The CFG edges were sorted by the counts achieved by PerfFuzz and the truncated data to show only the edges with execution counts within 2 orders of magnitude of the maximum hotspots found by PerfFuzz. The results confirm that PerfFuzz doesn't only work better with just maximum hotspots in the program, as across all of the benchmarks, 453 of the plotted edges are run across or exercised from PerfFuzz generated inputs 2 times more than AFL inputs, and for 238 plotted edges, PerfFuzz edges exercise them 10 times more than AFL inputs. It's just PerfFuzz is outperforming both SlowFuzz and AFL in every test. So SSLP then decided to manually analyze inputs generated by PerfFuzz in the test cases in a single run each to see where the hotspots were in the programs and how different inputs affected those hotspots. So we just saw that all these inputs generated by PerfFuzz executed close to or just simply worst case algorithmic complexity at all these benchmarks. So this table shows an example output and output from PerfFuzz with its work on libpng. It shows the top 3 CFG edges by execution counts for 3 of its most favored inputs. After every run, PerfFuzz outputs its set of favorite inputs, those that maximize the execution count of at least one CFG edge, and the execution count for each edge that it maximizes. So this table, for libpng, this table highlights different hotspots in the code. Just to show you what it would look like, I have a code snippet from PNG on the right here. It shows an excerpt from a function that performs PNG interlacing. The argument rowinfo contains data taken from an input file. This snippet shows 2 of the distinct hotspots, sets of input-dependent nested loops, guarded by a switch on an input characteristic. Thus, the inputs from the file are only instigating information for those hotspots. So for the first input, we can see input number 9189 with a pretty big execution count of 2,071,824 times. It maximizes the executions of an inner loop when pixel depth is 1 at line 315. A pixel depth of 1, by the way, would just be a picture with only a single color. Monochrome is, I think, the more official name for that. Input number 10520, which has a maximum edge count of almost 300,000, maximizes executions for the inner loop when the depth of the pixel is 4, which is line 3842, that second for loop. A 4 pixel depth would be an image segment of 16 color palette entries, but there are still other inputs that highlight completely different hotspots in the code in general. For example, input number 10944 with an execution count of almost 250,000 is attached to a part of the code that is affected by the height of the given PNG, declared in the PNG header, where each iteration is per row of pixels, and so a hotspot is highlighted with an exceptionally tall PNG input. With all these favored inputs, PerfFuzz has shown us some key areas of the code that affect the running time and performance of parsing a PNG independent of file size, such as the image's dimension and pixel depths, all of which are located in the header. So for libjpeg turbo, there were similar distributions of inputs where hotspots were related to JPEG image properties. An example of this would be when an input was an image with a 4x4x0 chroma subsampling with a huge number of columns. Most of the stress points were around arithmetic decoding algorithms. There we go. Arithmetic decoding algorithms. PerfFuzz was able to discover inputs that stress processing for both one-pass and multi-pass images. For zlib, compared to the image formats JPEG and PNG, zlib was relatively straightforward. Zlib actually has a very well-done program in terms of spreading its workload out, as there are a lot fewer hotspots in the code. However, PerfFuzz did find one input that really worked zlib. It was an input that had a compression factor of nearly 126 times the normal execution path of zlib, where the processing led to a rather long execution path with a ton of repeated loops and branches to a not very well traveled paths. They didn't go very much into detail on that, so unfortunately I have to move on. But for libxml, the inputs produced by PerfFuzz revealed what SSLP thought to be a quadratic complexity in its parsing process. The largest hotspot was the traversal of the characters of an input of a string in a string duplication function. So for a 500 byte input, there was a staggering 226,512 iterations of a specific loop. After a few tests, it became clear to SSLP that the source of the problem was when the mutated inputs were given, the program was printing out context errors of the jumbled and bangled up mutated input. You've seen these kind of inputs. I've shown you that like T lesson Q, P, whatever. And you could probably think to yourself that maybe these inputs aren't exactly what XML files are supposed to look like. You're not wrong. The funniest part about this input that was created was that the inputs were so wrong that they caused a program to run itself over and over and over and over again just to print out the same errors again and again and again. Basically, PerfFuzz learned about the program, learned with quotations because it doesn't really know anything about the program, enough to kind of just break the XML software. It highlighted the pathological behavior deep in the XML tree itself, showing that the error handling code was itself quadratically complex. In the end, these case studies indicate that the inputs generated by PerfFuzz led to non-trivial hotspots being uncovered. As well, in libxml, we can see that PerfFuzz highlighted potential inefficiencies in the performance of the program itself. SSLP believe, and I agree myself personally, that this analysis suggests PerfFuzz successfully produces inputs that created stresses on a program and highlights potential hotspots for the same program. And this information can be used for performance checks on these evaluated programs or any that PerfFuzz is used on. So we have to talk about some, questions that people might have about PerfFuzz or flaws you might have seen in PerfFuzz from this. So, like other software that creates these testing inputs, fuzzing tools and the like, PerfFuzz is bound to its success only by heuristics, using them to create inputs with pathological program behaviors. PerfFuzz is also a dynamic technique, which means PerfFuzz isn't actually perfect, as much as the name would like to suggest, and may miss a hotspot, or may even not find the worst case behavior for each of the hotspots that is discovered. This paper is also focused on discovering lines of code that are liable to repeat over and over again due to the increasing complexity of the inputs, thus measuring the execution counts instead of the total runtime. And this was decided as the main point of the paper, as it helps ensure that the measurements were accurate and deterministic, but there is a possibility that the identified bottlenecks are not where the code actually spends the most time. This problem could be mitigated by using a different cost model for CFG edges, choosing a new hit or a piece of the puzzle that would create bottlenecks in the code. For an example, would just be like I mentioned before, I/O operations. Instead of seeing if you hit that many edges, how many times, you just count how many I/O operations there are. Unfortunately, SSLP did not test any other cost models with other types of performance feedback like that. And finally, SSLP believes that the greedy techniques continually get stuck on local maxima, and PerfFuzz overcomes this, and thus being superior to the greedy algorithm users like slowfuzz by using non-convex performance space. While the testing with WF could be described as anecdotal evidence, SSL did not map the performance spaces of their benchmarks to measure their convexity. In order to do that, they would have to search through all possible mutations from each of the generated inputs, which, considering how many inputs I said were created within 6 hours, mutated or not, well, they're all mutated, but the originals are not mutated. All of them that are mutated, it's basically infeasible to go through all of those to find which convexity. So these are just some related things that work kind of similar to PerfFuzz. There's ForPost and GAProf. ForPost creates guides for itself to find a subset of inputs that come from a known input space, like a database of records from its own unsupervised learning. GAProf has a generic algorithm where inputs that would be regulated to be a specific way are encoded as genes. In contrast, both of these, PerfFuzz doesn't really need any knowledge about the program or its domain beforehand, and its coverage-guided feedback automatically discovers variety in the input space in order to explore deep program functionality. Both of these tools discover inputs that highlight performance bottlenecks in the software using repeated executions of the test program with candidate inputs. So yeah, PerfFuzz doesn't need any knowledge about the program or the domain beforehand, and the coverage guided inputs are just a lot better than repeated executions of the same given inputs. So then there's search-based software, SBST. This leverages hill climbing to optimize an objective function. Hill climbing, just a little brief aside, hill climbing is when there's an answer to an algorithmic question, like a specific answer, and then it is just changed in incremental ways to see what it does to the question, or in this case, program. If there's a specific way to run a program that makes it work the best, just change it a little bit. So it's kind of like mutation. This seems like it would work well, as it makes the inputs a lot smoother, just links the input a lot smoother to function. And it's a weird, I wrote this down weird, but basically what it says is it just makes the program run better because the inputs are a lot smoother. However, for general purpose programs, not ones that are specifically, hey, this is the exact answer, this obviously wouldn't really work well, and those are the type of programs that PerfFuzz is made for. Dynamic symbol execution, DSE. This generates inputs to exercise a given program path. WISE uses DSE to generate inputs that execute worst case behaviors. The problem with WISE is that it needs an exhaustive search of all the program paths to find the longest path up to a bounded input length. For programs with thousands of lines of code, this wouldn't really be a viable option. And finally, PerfPlotter is the last one they kind of mention. This fixes problems with WISE by using heuristics to find best case and worst case execution paths. And while PerfPlotter does seem like a good option over DSC and WISE, also known as WISE, it is still a single dimensional objective software. It's either total path length or total memory consumption. PerfFuzz can do both. It's multi-objective. It also generates a variety of inputs that exercise distinct hotspots in the program. So, just to wrap up everything, PerfFuzz is created to find inputs that create pathological executions of a program in order to identify hotspots in the code and highlight any algorithmic complexity failures. It does this by creating a performance map of each CFG edge in the program and keeps track of how many hits an edge would get with each input. PerfFuzz is given a set of seed inputs and uses favorability to choose which ones are to be mutated into children inputs. Those inputs are then run, and favorability again comes to see which of the inputs are made into parent inputs. This cycle will run execute with the execution of inputs, mutation of inputs, until the time limit is reached. With the researchers testing, pitting PerfFuzz against its biggest competition, SlowFuzz, and PerfFuzz's own parent, AFL, we can see that PerfFuzz outperforms the competition, sometimes only by 2 times the amount, other times there was at least 100 times better than its competition. SSLP also manually reviewed a few of the inputs and the hotspots they highlighted from PerfFuzz and walked us through how the inputs worked within the program to bring to light these hotspots. While PerfFuzz does work very well, it is not perfect, as because it is a dynamic program, it cannot always be 100% accurate in finding all the hotspots or the worst case behavior for each hotspot. It can also have gaps in its logic, but they could be remedied by changing cost models for the program, again, like IO as the cost edge instead of the edge itself. Most of all the tools related to PerfFuzz in one way or another still cannot perform quite the same tasks as PerfFuzz, or at least not up to the standard as PerfFuzz. And PerfFuzz is based in C and C++. However, I'm sure there can be a smart team that won't take very long to transfer PerfFuzz into Java or Python or any other non-C related languages. I don't think it'd be too long with the. It's on GitHub. PerfFuzz is on GitHub, so I think it wouldn't take very long for someone to translate that into, Java. Well, probably a team, into Java or any other non-C language. And that's really it. These are just the acknowledgments. It's just the full names of the researchers. I got all my information off them. I would like to thank everyone for coming to this presentation. This is going to be up on this new YouTube channel. If you're in my class, you had to come, so too bad. But if you're just strolling along and you find this, well, I hope you learned something today. Okay, everyone, have a good day.